Hello, my name is Paul Bemis, and I'm the president of Applied Math Modeling. Today I'm going to be talking to you about the evolution of data center design from the early days of the mainframes to where we are today with hyperscale infrastructure. In the early days of computing, dating back to the 1950s through the 1970s, computer systems, as shown in this image, were characterized by centralization with largely mainframes. That's what they referred to these machines are, and you can see why. They're very large frames here of equipment. Densities here were quite low. The rooms were air-cooled. There was little redundancy in terms of cooling. They were raised floor. You can see the raised floor design here. However, it was primarily used for cables. The cables that ran between these machines, referred to as bus and tag cables, is how they used to define them, were quite large and bulky. Power densities here were quite nominal, about 100 to 200 watts per square foot. Notice also there are people in the room. These were supposed to be office environment kinds of systems. And so the ambient temperature inside that room was fairly nominal and allowed humans to be in there without too much problems. As we moved into the 80s and 90s, we experienced something called client-server and enterprise computing. The environments became quite distributed. This was during the development of the microprocessor. And the microprocessor, particularly Motorola at the time, 68000s, together with enough memory and disk, able to build a local computing system, both in the form of workstations, typically run by Unix, or operating systems used Unix, which was a publicly available operating system developed at AT&T Labs, and also the mini computer. On premise, we had more data centers expanding. They got a little bigger, particularly the mini computer. A surge here for scientific processing drove this period. We began to see them arranged in terms of hot aisle and cold aisle. So the computers began to become aligned fairly well, although it did take some time for that to take effect. And we began to worry about cooling, in particular redundancy. So N+1 suggesting you have some extra cooling capacity, at least one extra unit, so that you can handle the effect if one of them fails. During this period, we saw rack density. Rack is an IT rack, so we saw densities here. Typically in the 4 kilowatt, 5 kilowatt range was normal for this. This is an example of one. This is an older IBM data center that we use for demonstration in CoolSim. This is an image from CoolSim. I'm using it here to show you a typical raised floor. Notice here we have underfloor cable tray. So during this period, there was still a raised floor. You can see the raised floor here. Cable trays were used to segment the cables and try to collect them so that they didn't become an obstacle to airflow under that floor. You can see these are downflow units. The little dot at the top is an arrow and showing you the air is going down through these units, past a fan coil, and into the floor and blowing into the room. This is generally what we refer to as perimeter cooling, because you can see the units, the cooling units are all on the perimeter of this room and blowing down into the floor. We refer to this as a naturally convective system because the heat coming out of the servers is going up and coming back to these cooling units into the top convectively, naturally. There's no ducting, there's no sealing plenum. The room is still mixed pretty heavily. There's no containment going on. Even though these are lined up now, you're seeing the beginning of them being lined up pretty well. The green arrow is airflow indicator, so front to back. You see the cold aisles here with perforated tiles in the cold aisles, the hot aisles on the other side. So the equipment in this section of the room is lined up fairly well with respect to hot aisle, cold aisle. However, it's not unusual due to evolution to see some not lined up perfectly well. This rack set over here is perpendicular. Furthermore, there are some other issues that this particular data center is facing. The red dots on the top of these racks indicate there are cable cutouts underneath them. So the cables are actually going to the rack in under the floor, which causes some leakage. You don't want the floor to leak. The floor should be sealed, but you do run into leakage in these designs. Furthermore, the rack equipment is awfully close to the cooling units. You see that on this side of the room. See a little of it right here too. This tends to cause problems because the velocities underneath the floor are high in this region. Remember that pressure, this is a pressurized plenum, and that pressure is made up of two components. Total pressure is equal to static pressure plus dynamic pressure, and they trade off with one another for total pressure. So as the velocity goes up here, coming out of these cooling units, you have a lot of dynamic pressure, but not a lot of static pressure. What we want in a data center, really, under that floor is uniform static pressure. Also, we have some tape drives over here. These are STK silos, if any of you remember those. These are tape drive backup units. There's other equipment in the room. The red blocks are PDUs, or power distribution units, typically transformers or some other method for getting power to the aisles. Racks are colored here in terms of density, indicating some kind of arrangement of different densities within the data center. This is an image from CoolSim of the performance of the floor tiles as a function of mass flow rate. You see here we're looking at cubic feet per minute, CFM, and you see the range here is from 492 to 942. We're seeing a factor of almost 2 in performance across that room. And you can see again, as I get close to a cooling unit, the performance of the tile, the airflow coming out of the tile, declines. And that's because, again, we have high velocity air coming out of this cooling unit under the floor. And therefore, there isn't much static pressure right here. It's primarily dynamic. In a perimeter design like this one, the static pressure is always highest in the center because all of the flows come to the center. Their dynamic velocity declines. Their static pressure rises. So the best place to put high density equipment in a room like this is right in the center because that's where the static pressure is the highest. Furthermore, positioning of the cooling units can cause some underfloor effects to occur. It is not uncommon to get low pressure areas in certain regions due to vortices under the floor caused by the positioning of the cooling units themselves. This is an airflow indicator. This is a CoolSim output map, and it's showing you a plot. It's showing you air coming out of the floor tiles. Now, what you would like in this case is to see none of these path lines. These are path lines of air. We simulate particles going through the air so that you can visualize it using computational fluid dynamics. And here you can see the cold air coming back to these cooling units. This is called bypass airflow. It's bypassing the rack. A perfect situation would be shown up here, where we have just the air coming out of the tile and into the rack. Not a lot of bypass going on in this region. But because the static pressure is highest here, as I showed you, we have more flow coming out of those tiles than the rack can absorb, and it goes right up over the top and into the cooling unit. This is bad for a couple of reasons. This plot is a temperature plot. We're looking at temperature as a function of color. And you can see it starts off blue at around 65 degrees Fahrenheit, but as it comes through that room and towards the return, which is supposed to be hot, you can see it's heating up. It's getting up into the 80s. This makes the cooling units less efficient. The way to make a good heat exchanger better is to provide a substantial delta T, change in temperature, between return and supply. Bypass airflow tends to cool off the return and therefore make the efficiency and the cooling capacity of this device decline. Furthermore, over here on this end, we can see some other things going on. You can see the air coming up out of these tiles at an angle. This is again due to the very high velocity coming from this cooling unit. And the upper regions of these racks are not being cooled properly because the tiles aren't delivering the air straight up. They're delivering it at an angle due to the velocity of the air in the underfloor. We made these transparent so you can see through the racks. These racks are full. We just turned transparency on so that we could show you that effect. This is an image of the return airflow. I'm going to show you this one in 3D because it's a little busy, but you see the air coming back to these units. These are the cooling units from the racks. I'm just going to open this in a 3D viewer so that you can view it a little more clearly. Sometimes rotation allows the viewer to understand what they're seeing a little more effectively. So here we have the hot. We're just looking at the hot air right now. You see the hot air coming back towards the cooling units as they should. But you notice that as the hot air comes back and it cools off, you see temperature dropping. We're looking at the temperature here ranging from 65 to 99. You see this cooling unit is being cooled off by the air that I showed you in the earlier image, mixing. There's mixing of hot and cold in this design. Because we are not using any containment, the hot and the cold mix together. And the problem with that is, again, efficiency of these cooling units declines as the delta T goes down. In other words, the return air is not as hot as it needs to be. We can also see some rack recirculation going on in this image, where it's actually wrapping around the racks towards the inlet. You can see it right here. So let's take a look closely at this image. You can see, as I turn this to the top, you can see that this rack is wrapping right around. The air is coming around the back of it and back in towards the inlet. This is called rack recirculation, and this occurs when the performance of this tile is not sufficient. The server must get its air from somewhere, so it effectively breathes its own exhaust. It intakes the exhaust coming out of the back of the rack around to the intake. There's one other area in this image where you can see a very similar thing. It's up here. Remember, these weren't performing very well, I showed earlier, and therefore you can see the air coming right up over the top of those racks and being inhaled back into its own intake, causing the performance of these racks in this region of the room to be poor. It is a misconception that putting the racks close to the cooling equipment is good. It can actually be bad because if you get it too close, these racks will recirculate. You can see here again it's recirculating around the end. That's because the performance of these perforated tiles is poor, and so the racks pull air from their own exhaust back around to the intake. Now, as we began to get into the 2000s, there was a lot of activity in the .com area, and cloud services became more prevalent. We had a lot of growth in co-location, where multiple machines and companies were sharing the same data center. Multi-tenant data centers is sometimes what they're called. We saw standards come along, particularly from people like Uptime Institute, N+1, N+2, sometimes having enough redundancy so that you can lose 2 cooling units and still work well. And also we saw some energy metrics begin to emerge. DCIE and PUE, those are the same metric. DCIE is presented as a percentage, and PUE is presented as an integer. In terms of density, 10 kilowatts was common during this period. That was a fairly heavily dense, heavily loaded rack was 10 kilowatts. And PUE is, again, this ratio. PUE is often 2.0. Now, in the numerator of PUE, you have the IT load plus the energy required to drive the cooling system divided by the sum of those two divided by IT load itself. So when you have a PUE of 2.0, it indicates that the cost to cool the data center is equivalent to the cost to power the data center. In other words, for every kilowatt you're putting into the data center, you're using an additional kilowatt to get that residual heat out of the data center. So 2.0 is not good. We saw an awful lot of this, however, during this period of time. This is an example, again, a cool example of internet-based co-location. Oftentimes, these are owned by different companies or leased to different companies within one data hall. These tend to be a larger, 20,000 square feet, couple thousand square meters is not uncommon. This one is using downflow again. This is a raised floor design. It is using plug fans. These are radial fans that blow the air horizontally a little more effectively. They don't just blow straight down, they blow horizontally, which gives them a little more throw into the room. You can see this one is cold aisle contained. So there are the perforated tiles. These are the racks. You see the whole section here is surrounded by containment that goes all the way to the ceiling in this case. And then on the hot side, we have ceiling grills. These are lined up so that they're blowing together against one another and up into the ceiling. So containment became popular during this period to try to separate the hot from the cold. You notice that the cooling units themselves have extensions on them that go up into the ceiling. So they're sealed up against the ceiling plenum. The return takes place in these grills. So the hot air comes out of the servers, up into the grills, back around to the cooling units, and back down into the floor. Cooling units is where the heat, of course, is dumped. It's dropped. Now, a couple things about this particular design. This is a cold aisle contained, which means that as you walk around in the room, you're standing in effectively the hot aisle. So these rooms tend to run quite hot. Typical delta T on a rack is during this period about 20 degrees Fahrenheit. So if your inlet temperatures were in the range of 70, that means your outlet temperatures are going to be in the range of 90 or greater degrees. So the temperature for humans in this room is going to be 90 degrees Fahrenheit to make these operate effectively. And that's fairly warm. IT loads in these kind of designs for upwards of 10 kilowatts per rack. But these also had some issues. Again, we have highest flow rate because we have a perimeter design. These are the cooling units on the perimeter blowing down into the floor. And so just like in the earlier representation, we have best performance in the center. Furthermore, you see some variation in performance here. These are usually caused by local vortices, vortexes that occur. So here we have the air coming out of this one and the air coming out of this one. There's a slight a bump out in the geometry of the room, and that's going to cause a general swirl here, and that will create a low pressure right in the center of it. That can be seen in this image. This is an underfloor image. It's a little hard to see here, but you can see I'm looking at the bottom of that same cooling unit. It's blowing this way. This one's creating a block over here. It's blocking the air from coming this way. The little bump out is not helping, and that creates a small vortex right underneath, and that creates a low pressure. Now, as we move forward to hyperscale and larger systems in the 2020 period, we see big designs. These are large data centers in general. People like Google and AWS begin to build these very, very large data centers. They become somewhat modularized, and they tend to move away from raised floor designs due to sheer size. The sizes are so big and there's so much air that needs to be delivered that it's practically impossible to get it through a raised floor design without having issues. So they tend to build these as non-raised floor designs. We are also seeing something called free cooling. Free cooling is the idea of using outside temperature. Often it is done through what's called a dry cooler, so it's a heat exchanger. Sometimes they also just use straight outdoor air. That's popular in the field of cyber computing, is to use straight outdoor air. We're also seeing the reintroduction of liquid. Liquid cooling is much more effective, of course, than air cooling, but it's also more expensive. However, the densities are getting high enough so that we're beginning to see liquid come back into use for these kinds of systems. We're also seeing data center information management tools be used more heavily during this period, looking at how much power is being pulled by each of the units, monitoring them for processing capacity. And during this period, we begin to see racks, IT racks, go up into the 20 kilowatt range, or even possibly higher. This is an example of one of those kinds of designs that we see quite a bit here at Applied Math. These are cooling units. These are what are called fan walls sometimes. So let me just again go through the flow of air. There's a fan coil in these blue entities, and the air comes out and into the room. These are the racks, of course. This is containment, in this case hot aisle containment, which is a little more preferred from a human point of view or an environmental point of view for being in the room. You contain the hot, that's a little better on people who are in the room. Here are the racks. You can see this rather orange looking surface is a leakage component that allows you to predict the leakage through the containment. Pressure leakage in this case, causing performance issues sometimes. Ceiling grills at the top. So the air comes out of these blue units through the racks into the gray containment, up through the ceiling, back around through the ceiling grill. So the return plenum is above. So the top of the building or the top of the room is defined by this green line. Goes back up over the top and around in a circle. So the air circulates in this direction. The reason they do this is to try to get the velocities down. You want as low a velocity as you can get on these units. So the bigger they are, the lower the velocity will be. Remember, you want static pressure, not dynamic pressure, so low velocities are good. And because these racks are now getting so dense that the amount of air required is fairly large. So you need more of it. Raised floor becomes prohibitive because the velocities are simply just too high if you try to use a raised floor. Cross-sectional area is too low, causing high velocities. And so here they're using very large fan walls to try to get that down. We're seeing densities in these racks now above 30 kilowatts, upwards of 40, 45, 50 kilowatts per rack. And this is largely driven by the artificial intelligence phenomena, which is causing rack densities to go up quite dramatically. This is a view, again, of path lines of supply air, showing you how the air is coming into the room as a function of velocity. I also have this one in 3D that I can show you, so it's sometimes easier to see it in 3D. You can see the air coming out of those cooling units. And in some cases, it has to bump into the edge of the contained area for the rack and go around it. This causes a pressure surge to occur right here, so static pressure goes up quite high. And when it comes around a corner like this, it also causes the velocity to rise. You see the velocity in this cold aisle is fairly high. It's in the range of 400 feet per minute. This high velocity causes pressure variation sometimes between the hot aisle and the cold aisle, making leakage occur through this region. This is the seal between the racks. This is often the inside of the rack or where the rack seals against the containment. And those are areas that can leak pressure. And when they do, there's sometimes recirculation that occurs around the rack itself. It's exacerbated by this phenomena where the high velocity air comes out, bangs into the containment, and then has to wrap around the edge. It combines with other air to cause a high velocity region in the cold aisle. The goal of these designs is that the room should always have higher pressure than the contained area. The idea is to produce a positive delta pressure between the inlet and the outlet. In this case, the area that is here in blue should be highly pressurized, or at least somewhat pressurized compared to what's in the hot aisle. But that's not always the case. On a localized basis, you will get these variations. This is a velocity plot. We're looking here at velocity as a function of color, same data center. And you can see the velocities are quite high when they bang into this edge right here and wrap around it. You can see the velocity surge right on the edge of these are the servers. You see that velocity surge. Velocity goes to 0 when it hits the edge of that containment. So it comes out, bangs into the containment, and begins to wrap around the edge, causing pressure variations right here. You can also see some fairly high pressure in the contained area itself. Even though in this particular design we're supplying more total air than is being consumed by the racks, and therefore you should have a positive pressure differential across the rack everywhere in the room. But it's not the case, because what happens locally is these two streams of air coming out of the back of these servers bang into one another, so their dynamic pressure goes to 0, and the static pressure goes up. And that's what we're showing you here is high static pressure. And in this case, we're seeing a velocity surge. This is at 6 feet, so we're seeing the air coming up out of the rack and into the hot aisle. That's why it's high there. Another plot here, this is pressure. We're going to show you the pressure variation. I have this one in 3D as well, so you can take a look at this a little more clearly. So here's the pressure variation, and again, we're seeing the same effect. So watch what happens in pressure. Velocity and pressure are basically synonymous to one another, but here's your high pressure, and here's your low pressure right here being caused by the high velocity coming around the edge of that, causing a delta P across the server that is not advantageous. If this gets high enough, it'll actually cause this server to be hot. You'll get hot spots in the server because the velocity going by it is creating a very low pressure on the front end, and that delta P is so high that it simply cannot pull the air into the server, and you begin to what we call walk the fan curve on the server. In other words, the delta pressure across the server gets so high that the fan can no longer deliver air. The analogy is putting your hand over the end of a vacuum cleaner. The motor's running, but there's no air moving. And you can begin to get into those kinds of problems occasionally if the distance, again, of this device is so close to this supply device that it causes this to occur. So I thought I'd show you the pressure. Again, pressure in the center going high. What's interesting in this design is, again, we're supplying more air to the room than the racks need, so you would logically think that the room is always going to be positively pressurized compared to the containment. Not the case. You noticed here that we're seeing just the opposite, that in the contained area, we are seeing pressures higher than what is in the cold aisle. It's backwards. That's due to velocity. The velocity will do that. Here we're seeing the two air streams hit each other, and we're seeing pressure rise as a result of it, static pressure going up. Here we're seeing high velocity air go by, static pressure going down. This is a plot of static pressure. So it manifests itself in the thermal characteristics of the room. If the pressure deltas aren't correct, you'll get leakage. That's what we're seeing along this edge is leakage. This is leakage from the hot aisle into the cold aisle through the surfaces that seal the IT servers against the rack. Right here you see leakage. You see it's starting to poke out. It's bleeding out because we don't have enough positive pressure between the cold aisle and the hot aisle. So the hot aisle is very hot, creating high pressure, and you've got velocities going to 0 in there, creating pressure, and it causes this to occur. We also have this one in 3D, and it varies throughout the room. In certain places it'll be fine, other places it'll not be good at all. So let's take a look at a few of those. We zoom in on it, and you can see leakage will vary across the rack depending upon the rack row, depending on where you are. In certain places it'll be worse than others. This manifests itself, so it's not so bad here, but not good over there. This will manifest itself as higher rack inlet temperatures. Rack inlet temperatures are governed by the ASHRAE 9.9 specification. And that is 80.6 on the inlet for recommended temperature inlet Fahrenheit. So you can see leakage here. And this is how we model leakage in CoolSim. We set these up and then take a look to ensure that you have sufficient pressure differentials to be able to make the data center behave itself appropriately. So as we move forward in time, what we're seeing is more sensitivity to energy, carbon reduction, renewable energy. We're looking at load modulation. One of the things we see coming is the idea of modulating the IT load to be sensitive to the grid, scheduling load to occur. There will be economic incentives for that. So there will be often signals sent to the data center that if they curtail power consumption, they can get a benefit in cost for the power. And so they will begin to do that intelligently. We are also going to see a lot more liquid. It's required. There are 3 methods. Direct to chip, where we bring liquid right to the heavy consumers of power. Those typically are the AI chips from NVIDIA, as well as the microprocessor chips. You will still need air cooling, however, because all the other chips, including the dynamic RAM, the controlling systems, the controllers of communication systems, and the disk and the power supply will continue likely to be air-cooled. There is also a rear door heat exchanger. This is very much like the heat exchanger on the front of your automobile. It is a basic fan coil kind of structure that sits on the back of the racks and will pull heat out. There is also a technology called immersion, where you put the entire rack into liquid and you cool it that way. That one tends to be very expensive and not widely used today. And you're seeing an awful lot of workload-ready infrastructure, equipment coming with the NVIDIA chips already deployed in them and ready to go with liquid cooling technology already ready to be attached to the cooling distribution units that are required to pump the liquid through the system. We see automation coming. This is all part of artificial intelligence, is to automate the task of load scheduling and load management, as well as predictive and preventative maintenance. So as we go forward, we're continuing to see, AI-powered facilities running somewhat on their own using machine learning to optimize the run sequence with respect to time, particularly considering power coming to it from the grid. There's a lot of sensitivity about carbon neutrality and energy efficiency of these devices. In these data centers, I think we'll see a greater use of renewables and storage here being battery storage to power these data centers. Renewables are attractive, particularly renewables like solar with battery are very attractive from a cost point of view and also from a rapid deployment point of view. If we're going to meet the surging demand of these data centers, the quickest way to achieve that is using renewables, because they can be deployed quickly and are fairly inexpensive. They are, again, solar wind being the lowest cost of generation in the world. And we're going to see some quantum computing, which is going to require cryogenics. That is another energy issue. Cryogenic computing, very cold, of course, and therefore, whenever you make something cold, it takes a lot of energy. And more tightly connected, lower latency, higher bandwidth interconnects between edge computing and core systems. And the focus shifting for us here, our job is to help predict heat transfer, in particular of these devices. Exterior. We have been fairly efficient getting the heat out of the data center over the years, and now it's outside. And the issue of how these heat exchangers outside of the building, typically on the rooftop or beside the building, behave under prevailing weather and wind conditions becomes quite important. The issue of cascading hot air coming into the intake of downstream chillers is becoming more of an issue as densities rise, because there's just so much heat coming out of a data center. Being able to dissipate it across an environment, an atmosphere, given the specific location and wind condition, is becoming challenging, and we see quite a bit of work in the field of modeling, CFD modeling, to optimize the dissipation of heat into the atmosphere. So that's all we had today. This presentation, I want to thank you again for being here and watching this. If you'd like to reach out to us, Applied Math Modeling or coolsimsoftware.com, and you can ask questions or get in touch with us. Thank you very much.